Hello friends, welcome to Yantriki. Today in this video we are going to discuss about heat exchangers. An increased demand for energy and environmental issues on a worldwide level have stimulated a number of researchers to work on improving the efficiency of thermodynamic cycles and look for ways of utilizing renewable energy sources. The organic Rankine cycle is a suitable technology for employing low-grade temperature heat from several renewable energy sources. In order to be able to operate at supercritical conditions, proper heat transfer correlations need to be used. Hence, to provide accurate correlations for the heat transfer process of the working fluids under supercritical conditions, we need to design an optimal heat exchanger. If we go by the definition, a heat exchanger is a device used to transfer heat between solid object and a fluid, or between two or more fluids. The fluids may be separated by a solid wall to prevent mixing, or they may be in direct contact. In short, it is a device for transferring heat from one medium to another. If you go by this diagram, you can see that the condenser here in this diagram is acting as heat exchanger because the heat coming through the expansion valve is released in the condenser. The heat exchangers are widely used in power stations, chemical plants. If you could see in this pictures, power plants, chemical industries, petroleum refineries, refrigeration and air conditioning. Heat exchangers are used widely. There are many other industries like petrochemical plants, space heating, natural gas processing, sewage treatment, which utilizes the heat exchangers. The classic example of heat exchanger is found in internal combustion engine, in which a circulating fluid known as engine coolant flows through the radiator and air flows past the coils, which cools the coolant and heats the incoming air. Another example is the heat sink, which is passive heat exchanger that transfers the heat generated by an electronic or a mechanical device to a fluid medium, often air or a liquid coolant. There are three primary classifications of heat exchangers according to the flow arrangement. Here in this figure, we can see counterflow, parallel flow and cross flow. In counterflow heat exchangers, the fluid enter the exchanger from opposite ends. The countercurrent design is the most efficient in that it can transfer the most heat from the heat transfer medium per unit mass due to the fact that the average temperature difference along any unit length is higher. Fluid flows in opposite directions and are used for liquid-liquid condensing and gas cooling applications. Units are usually mounted vertically when condensing vapor and mounted horizontally when handling high concentration of solids. In parallel flow heat exchangers, the two fluids enter the exchanger at the same end and travel in parallel to one another to the other side, thereby minimizing the temperature differences. In a cross-flow heat exchanger, the fluid travel roughly perpendicular to one another through the exchanger. This type of flow is suitable for handling low-density gas, which passes through the cross-flow, avoiding pressure loss. It can be used for liquid-liquid applications if one liquid has a considerably greater flow rate than the other. Double pipe heat exchangers are the simplest exchangers used in industries. Here you can see tubular heat exchanger where there is one tube within another tube. However, the structure at the top is known as shell and the one within the shell is known as tube. On one hand, these heat exchangers are cheap for both design and maintenance, making them a good choice for small industries. On the other hand, their low efficiency coupled with high space occupied in large scale has led modern industries to use more efficient heat exchangers. Therefore, we are using shell and tube or plate heat exchangers. However, since double pipe heat exchangers are simple, they are used to teach heat exchanger design basics to students, as the fundamental rules for all heat exchangers are the same. There are multiple heat exchangers available. Example: shell and tube heat exchanger, plate heat exchanger, plate and shell, adiabatic wheel, plate fin, pillow plate, fluid heat exchanger, spiral heat exchangers. However, we will discuss about some of the basic heat exchangers. First of all, we will discuss about shell and tube heat exchangers. Shell and tube heat exchangers consist of series of tubes. One set of these tubes contains the fluid that must be either heated or cooled. The second fluid runs over the tube that are being heated or cooled so that it can either provide the heat or absorb the heat required. A set of tubes is called the tube bundle and can be made up of several types of tubes: plain, longitudinally finned, etc. Shell and tube heat exchangers are typically used for high pressure applications with pressures greater than 30 bar and temperatures greater than 260 degrees Celsius. This is because the shell and tube heat exchangers are robust due to their shape. Next to it is plate heat exchanger. These are composed of many thin, slightly separated plates that have very large surface areas and small fluid flow passages for heat transfer. Advances in gasket and brazing technology have made the plate type heat exchanger increasingly practical. In HVAC applications, large heat exchangers of this type are called plate and frame. When used in loops or open loops, these heat exchangers are normally of the gasket type to allow periodic disassembly, cleaning and inspection. There are many types of permanently bonded plate heat exchangers such as dip brazed, vacuum brazed and welded plate varieties, and they are often specified for closed loop applications such as refrigeration. Plate heat exchangers also differ in the types of plates that are used and in the configurations of those plates. Some plates may be stamped with chevron, dimpled or other patterns, where others may have machined fins or grooves. Plate heat exchangers also come with plate fins. Plate fin type of heat exchanger uses sandwich passages containing fins to increase the effectiveness of the unit. The designs include cross-flow and counterflow coupled with various fin configurations such as straight fins, offset fins and wavy fins. Now we will discuss about helical coil heat exchangers. These are gaining wide importance nowadays because it can give high heat transfer coefficient in small footprint of surface area. This design is that of a condenser and is usually mounted vertically. It is designed to cater for the subcooling of both condensate and non-condensables. The coolant moves in a spiral and leaves via the top. Hot gases that enter leaves as condensate via the bottom outlet. Now we will discuss about spiral heat exchangers. It's a modification to the perpendicular flow of the typical helical coil heat exchanger, which involves the replacement of shell with another coil tube, allowing the two fluids to flow parallel to one another, and requires the use of different design calculations. These are spiral heat exchangers, which may refer to a helical coil tube configuration. More generally, the term refers to a pair of flat surfaces that are coiled to form the two channels in a counterflow arrangement. Each of the two channels has one long curved path. A pair of fluid ports are connected tangentially to the outer arms of the spiral, and axial ports are common but optional. The spiral heat exchangers can be fitted with different flow arrangements like counterflow arrangements where fluids flow in opposite directions, parallel flow arrangements where fluids will flow in the same direction, and cross flow arrangements where the fluids will cross each other. This design is that of a condenser and is usually mounted vertically. It is designed to cater for the subcooling of both condensate and non-condensables. The coolant moves in a spiral and leaves via the top. Hot gases that enter leave as condensate via the bottom outlet. Now, we'll discuss about the selection of heat exchanger. To select an appropriate heat exchanger, the system designer would firstly consider the design limitations for heat exchanger type. Though cost is often the primary criteria, several other selection criteria are important, like high-low pressure limits, thermal performance, temperature ranges, product mix, pressure drops across the exchanger, fluid flow capacity, cleanability, maintenance and repair, materials required for construction, ability and ease of future expansion, material selection such as copper, aluminum, carbon steel, stainless steel, nickel alloys, ceramic, polymer and titanium. So these are the points which we need to keep in mind before using a heat exchanger. Thanks for watching.